Hi guys, so in this video we will going to implement transformers architecture. So this is the transformer architecture. You probably have heard of it. If you haven't read this paper, Attention is All You Need, which is very famous, please read that. And we will going to implement the transformer architecture. In previous videos I implemented the attention and multi-head attention, but we will going to implement the whole transformer architecture and train on our small data sets and see how this goes. So yeah, let's go. Let's start importing things. So import torch, import from torch, import nn, and from import math. Okay. Yes, so now we have to implement the positional encoding. So in the transformers papers, you have this positional encoding. This is the positional encoding. Basically, it's the non-learnable embedding kind of thing. Let's implement positional encoding nn.module. So it will contain actually the two arguments. The first is t model, which is the model dimension, and the second is sequence length. So it, like as a default I'm setting to 100. Okay, and here we going to just do some formality with Python. Inside this there's this we have to first initialize our positional encoding, and the easiest way to do so is to torch.zeros, and this will contain the shape of sequence length and d model. So the length of the sequence, one sequence of length, and then the dimension of the model. Div term torch.exp, and then because it's two times of it, it's a two times of it. So if I go here, it's 2i divided by d model. So torch dot arrange and start with 0. Arrange function will do like it will, if I am just doing torch dot arrange, arrange, I'm just gonna show you here. Import torch. If I go torch dot arrange, and from 0 to 100, it will just like give a tensor which will go from 0 to tensor, right? So this dot arrange will 0 to, and we have to go two times of it. So it will go to the d model first, but twice the steps. But here you will see like if I go 100, twice the steps, like this, 0 2 4 6 8, but the total length will be, if I share this, it will be 50. And that's good, like, because this thing, this div term, which we will going to divide it by position, has to be the half, because first we have to do it with sine and then the cos. So the half of this will go to even thing, and the half of this goes to cos, the odd thing. So I think this is very good for us, so we don't need to actually do anything here. And then basically, because of the identity, I can just like go and do the multiply with negative of math dot log of 10,000, and I can divide it d model. I can also divide it here, but like it's exactly the same. So we got this div term. Now we have to define the position. position is basically the position of the tokens, and we can just like define it like this: position dot arrange, because position is just index, 0th, first, second index. What is the position of these tokens? So the position is, it will start as from 0 to sequence length, right? And unsqueeze it, unsqueeze the first. Well, why first? Because the position where, wait, let me just do it right way. What the hell? Position, okay, yeah. Position. Why we did that? Because, you know, if you look at the matrix multiplication of it, because we were going to do the matrix multiplication, it's basically the matrix, right? This is the matrix, this is the matrix. And why we do that? Because sequence length, I think it will go to sequence length, and we have just did 1 because unsquared it in the axis of 1. Let me show you. So if I go, if name equals to main, position encoding, system model 512, not sorry, 128, sequence length 100, and you know, PE, call this thing with a rand, and this will get like a sequence of let me just give some simple 100, not 100. This will have like a encoding, but like it gets the embedding of the, and it will combine with the position encoding. So it will have first is batch size, right? First is batch size, and then it is 128, which is the sequence length. That's it. And let's see, div term dot shape. Wait, let me just go here. Yeah, it does require forward function, so we can just like do it like this. So it has a shape of 64, so it will, when it will multiply, which is a matrix multiplication, not this, but I can just say this, multiply with 64, which is like a 64. So it will have a equals to sequence length and 64. This will be treated as like 1 because of the broadcasting PyTorch. So yeah, that's why like I'm unsqueezing it. So I hope you got what I'm trying to do here. Then in the forward pass, basically, not yet, we haven't yet built our position encoding yet. So as we know that in the even side it will contain the sine function, and in the odd side it will, odd index I will say, not odd side, odd index, it will contain cos function. So PE, we just need to provide the right information in the zeros, because it's right now it is 0, so we'll just go and like put the real information. So ignoring the 0th index and going to the first index, and here in the first index we can just 0, and taking step 2 equals to dot sign and position and div term, and same do for this cos thing, starting with 1 and taking step 2 dot sign cos position div term. Basically we are doing the dot product here, not a matrix multiplication. So because this thing in PyTorch will do the dot product. Okay, so the next we have to do is implement the forward function, and the x here is basically it is coming from the embedding layer, and it has a shape, you know, it has a shape of batch. The first is batch, sequence length, and demodel. What we need to do is add this actually, because in the original paper they are adding this input embedding with positional encoding. So x equals to x plus position, I guess, with self dot. The self dot p is not available, guys, because you know I have to do register buffer. Nice. Well, to make it more safe, I can just do like this till the sequence length, and sequence length will come from here. How this? That's why. Like, I thought, like, where I have defined the sequence length, it's actually imported automatically. I don't know how. So sequence length, I hope I'm audible. So sequence length x equals to x plus self dot pe, and x sequence length equals to x dot shape of 1, right? It will give us the sequence length. So unsqueeze it because it's not squeeze p0 width, yeah, and return the x. Let's see if it's working or not. I think it should work. Print x dot shape. Yeah, it's working. So our the output shape here is basically batch, sequence length, and demodel, right? So yeah, we have implemented the positional encoding. Now it's time to implement the multi-head attention. So for the multi-head attention, class multi-head attention, it's basically, if you go more specific, it's not multi-head attention, it's multi-head self attention. So we have constructor here, and in the constructor we can pass demodel, which is a dimensional, it's obviously required everywhere, and number of heads. So let me define number of heads first, and super formality with PyTorch, right? Multi head self attention, self, and then we have we need to basically define our QKV, security key value parameter. So QKV is nn.linear, and this is demodel and demodel. So I have combined the QKV in one linear layer and outputting as 3 times of it. So we can extract the QKV each of it because it's the 3 times of it. Well, because it's not just one head, single head attention, it's a multi-head attention. So we need to do some like broadcast, like some reshaping stuff, which is I will explain. First define this thing, number of heads, and number of heads, then D model, right? So this is like the QKV, the in projection layer, is act as an in projection layer also. We can go and produce out projection layer. Out projection means like it will spit out the actual thing, like after doing the attention mechanism, attention scores, there's another layer like out projection we are actually adding, which will just internally it will act as a like a adapter, you can say, and adjust some parameter. Nice. In the forward method, I think we have left few things, scale, which is the math dot square root of D model. But here we are doing D multi-head attention, so D head, and D head is basically, which is the dimension of head, because it's a multi-head attention. So in a single head attention, we have single head, which will do all the attention computation. So it contains dimension of the model, but because we are splitting it into multiple attention, it will go to the one, each of the heads will get their own dimensions and tensors, which will be split out. So self dot sorry, not attention, but D head, which is the number of D model divided by number of heads. Right? Yeah. But if we can assert it if it is not divisible by number of heads, because it should be divisible by, otherwise like it will break. It should be like compatible enough to just split out in equal way. So assert D model number of heads equals to 0, otherwise D model should be divisible number of heads, or I can just say n heads, right? This is X, and this X is coming out of positional plus embedding layer. So the combination of those, which will just like batch sequence length and D model. Coming out of embedding plus positional So basically we have to divide it into multiple heads, and then each head will contain their own attention computation. So the input dimension is this, and the intermediate dimension, like in between the output and input. Output should be the same. So out should be batch sequence length demodel. So output should be the exactly the same as input, but in between we need to just reshape it to make it compatible to run on multiple heads. So intermediate shape is basically you have this batch and the number of heads. Number of heads will contain sequence length, and then sequence length contain a demodel, right? So right now the first thing we have to do is like do the forward pass with QKV, our in projection layer. So QKV self dot QKV X, right? And now this is sequence length demodel, and demodel the thrice of it. Okay, it's the thrice of it. We can define shape here. So batch sequence length demodel start shape, and then we have what we can do next is we need to reshape it right now. So QKV dot view batch size thing. So 3, and then we have sequence length number of heads dot n head self dot demodel d head. Sorry, let's see if it is working. I hope like it should work. Right, it should work. Attention the attention number of heads is 4, the model is 128. Dot random, and this random contains the batch size, which is 4, let's suppose, and not just 4, like batch size could be 8, and sequence length is 32, 128 as the demodel, right? And that's just print it. Okay, so 8, 3, 32, 4, 32, it is working. So batch size and 3 is the like our 3 things: sequence length, self dot heads, and self dot d head, right? But I think what I'm thinking is that this sequence length should be here and this 3 should be here. Why? Because this view changes and reshapes things, but it does not reorders the memory thing, because we have done the in projection layer here. So it can make it like the shape we have described it, but like the memory or the things inside this QKV have gone through will not gonna change it. So I'm just like trying to do like just reshaping the last 3, not touching these 3. So like just I'm gonna do just reshape the last dimension here and make it like expand it like in 3 extra shape, and this 2 will be like exact same. To make it more, to change the memory, change the inside the inputs of it, we can do something else, which is QKB equals to QKB dot permute, and that will basically where we can define index and change the indexes of it. Okay, so 3 batch size, sequence length, number of heads, sequence length, and heads. I can just rewrite it like this. QKB right. So this is how it should be supposed to be. If I go and run this, yep, 3, 8, 4, 30, 32, which is like exactly what we have done. Then what we need to do is, like, we have defined our QKV and made it into like a shape which can actually have multiple heads. And then we can extract Q and K and V now. So Q, K and V, QKV, QKV of 0 width. That's why we wanted this 3 to be the first, because now we can easily extract it. QKV first, QKV second. Nice. And then we can do our like the attention computation simply. So dot matmul q dot q and k dot transpose. This should be transpose -2 -1 attention, and then we have to do dot attention divided by dot scale. Sorry, self dot scale, I guess. Yeah. So the next we have to do is to apply masking, because in autoregressive state where we predict next token and transformer predict next token in a sequence, we want to prevent it to see the future tokens. So we mask the future tokens and we only show what is current context and predict the next token, and the next token is visible and the future token is again it's not visible. So yeah, this is the case. To apply masking in an easy way, we have a method in PyTorch, dot ones sequelength. This will create a sequelength dot ones, and dot drill will apply mask. Not apply mask, but creates a mask which exactly look like this. So 1 0 1 0 1 0. So this one is, you can see like the zeros are the masked, and it will create it like a triangle structure. That's why TRIL. So 1 is this, and then 0 0 0. And then next row you can see 1 1, and then 0 0 0. Next row 1 1 1 0 0. So as the model predicts the next token, it will only be the masked are only those which are not in a current context. So the future tokens are always masked. Got it? So this is how you do that, and then apply the mask. So attention dot masked fill mask equals to 0. So where the mask is equal to 0, apply the mask there, and the masked value going to be -inf. Okay, well, this is, it should be, so this is how the masking should be done. Like attention is dot softmax, attention is dot matmul, and attention and k. So this has a shape of batch, number of heads, SQL length, and d head. As we know, like, we need to our output going to be same as this, right? Our output is going to be same as the input. So out equals to be going to be this shape, and we need to reshape it to make it happen, because our attention computation is done. We wanted a number of heads and multiple heads only because of attention computation, and it's done, so we don't need, and we can just convert our attention scores back to normal. So basically we have to concatenate this heads into this d head. First, what we can do, we can just swap this number of head and with sequence length, and this can be done through attention dot transpose attention, sorry, to 1, right? And then contain, what was the, yeah, contain, wait, I have to check. Yeah, it was this. So contagious. So it basically, as I have explained, the reshaping of this and transpose of this will not gonna change the rechange or reorder the memory. The value, it will going to reshape it, but we want the attention scores and all the information should be intact like how it was. So we want it to be in the right order, and the memory should be exactly as same as, it should exactly swiped out. So that's why we did that, and contagious which help us to do that. After attention, we can just reshape it. attention dot view that sequence length demodel, and in the output of it we can just do lm head, right? This was lm head, oh sorry, not lm head, it is alt projection, yeah, return alt. Nice. Now we have implemented the multi-head self-attention. We can now create our transformer class and combine all these components into one. Number of heads, it will contain number of heads. The vocab size, okay, and then we have d model, number of layers, and sequence length, which is 100. So self dot embedding, and then dot embedding, and that will have a shape of vocab size and d model. Then we have positional encoding, d model, sequence length. Then we have our blocks basically, and blocks are the transformers blocks. So transformer block, which will contain like d model and number of heads, and d model for number of layers. Yeah, and layers. And then we have our lm head. Lm head is basically the spit out thing. So if I show you here, like here you can see, like after the transformer block we have this linear layer, which is like the lm head, or some kind of out projection layer, you can say, right? Yeah. Okay, so nn dot linear, and this will contain d model and vocab size. Okay, so it will spit out the vocab size. Then we have our forward method, x is shape. That shape will be basically, it will come out, it is a input IDs coming out from tokenizer. So x equals to embedding, self dot embedding, x equals to self dot positional encoding x, and then we have for layer or for block in self dot blocks, x equals to block. Then we have our self dot lm head. This will be x, right? So the output shape will be batch, sequence length, and vocab size. Now we just need to implement our transformer block. And dot module, number of heads, and d model. I guess I'm just typing so crazily. Super, wait, I forgot the super here too. Here basically in transformer block you can see like there are many things like feed forward and add normalization stuff. So we were going to add based on our own implementation. So the The first is layer norm ln1 it where one nn dot layer norm d model dot we have attention, so multi-head multi-head number of heads d model self.mlp multi-layer perceptron, which will be just sequential ReLU function. Yeah, then we have again linear layer and the model. Nice. Yeah, and there's another layer norm. Then we can define our forward pass. That x is basically, x is what? X is the shape of batch, sequence length, and the model. And this will be a residual layer, so it has a skip connection. So that's why I'm like x plus self dot attention, and that attention is basically getting the input from the layer normed output. And then we have this MLP, right? Return x. Nice, we have implemented our transformers. Congratulations. Okay, that's it. And yeah, in 142 lines of code the transformers is implemented. Well, we can just test it. Name equals to main. You can do you can do input IDs equals to dot and then 0 to 100, 0 to 1000 the vocab size, right? And have a shape of like this. Shape of the batch size is 4, let's suppose 4. So this is the input IDs, and then we have this model transformer, number of heads, let's suppose 4, vocab size is 1000, d model is 128, number of layers is 6, let's go, and sequence length should be 100. Okay, now if we do this, print model dot model input IDs dot shape. Okay, wait. Transformer. No, my dear name transformer. Why is that? Okay. There's error but it is coming from here. Invalid combination got expected after and but the issue is softmax. Okay, softmax dimension -1. Let's do again. Yeah, that's very correct. Yep, it's working. It's perfectly working. So I have a one task I have actually built, which is the um, you have we will give a small task to test whether this transformer is learning or not and implement it correctly or not. So there's this task which I'll just gonna copy and paste because it's I have prepared the data set and stuff, you know, and I'll explain you the task. So what we are doing here, so here basically we have this vocab which is our data set, and it contains a b c, and the interesting thing is that we can just test our transformer with just these three vocabulary inputs. So I have defined like char to index, which is like character to index. It will convert this a to like all these alphabets to input IDs, right? And then index to char, which will help us to navigate from index to characters again. So like it will help in decoding and this will help in encoding. This is length of vocab size, and our text is basically a pattern. ABC multiplied by 10,000 means that the text will contain ABC, 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 and like it will be like just a ABC, 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 ABC thing. And the transformer has to find out has to predict the next word based on what pattern it is learning and it has learned. So if I provide B, then model should learn to predict C because this is our pattern. If I provide A, after A there's B, and if I provide C, it should predict A because the pattern is ABC, 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 and ABC. So, and this is a training loop where we are basically calculating the logits, loss function, and then doing the evaluation. Let's test this. Okay, there's this sequence length, number of heads. Yep, you can see it is actually printing all its steps. So you can see like step 1, it has learned nothing. So it's just like A, B, blah, 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 like all these random predictions. But after learning, in step 2, it is quite better. Step 3, it is more better. After many steps, in the last steps, A, B, C, A, B, C, A, B, C, it learned pretty good. And if I print like loss function, so instead of this, if I print loss function, yep, so we can see like the progression of loss function, and the loss is that it is going down. So yeah, I hope guys you like this video. This was all about the transformer implementation, and I will implement more different kind of architectures. So yeah.